Last class, we left off right before we got to temperature. So we were talking about energy, we were talking about exothermic processes. Exothermic processes, energy is being released. So things like a hot cup of coffee cooling down would be exothermic. The coffee is going from higher energy to lower energy, higher temperature to lower temperature. Things like ice melting is endothermic because the water needs to gain energy to go from the solid state to the liquid state. I have a graph that I like to draw. It's just got one axis, and this one axis is energy or temperature. You can think of them as, they're basically the same. And on this graph, we put our three states of matter. What's our lowest energy state of matter? What's our coldest state of matter? For anything. Solid. So like ice, right, is the solid state. And then more energy than that is our liquid state. And then more energy than that is our gas state. And so if we think about, particularly for our state changes, our phase changes, like water boiling, when water is boiling, it's going from the liquid to the gas. It needs to gain energy to go from a liquid to a gas. So it's absorbing energy, it's gaining energy. So that makes it an endothermic process. If we've got something that's going from a liquid to a solid, like this ice forming on a pond, it has to go from this medium energy state to this low energy state. It needs to lose energy. In order to lose energy, it needs to release energy because it can't just disappear the energy. It can't just get rid of it, make it poof, go away. And so that's an exothermic process. So this can be helpful for doing things like this. It'll also come up again when we talk about solubility in a couple months. So that might be a helpful tool for thinking about, especially with state changes. Is it exothermic or endothermic? Draw out a quick little graph or think about it, and that might help you get the answer. Okay, moving on to temperature. Everything is in constant random motion as long as it's above 0 Kelvin, which is everything. And those things contain thermal energy. Temperature is a measure of thermal energy. The hotter an object is, the greater the random motion is, and the higher the temperature. Thermal energy and temperature go hand in hand. Temperature is different from heat. So heat is another concept that we'll talk about. We'll see it in an equation today. Heat is the flow of thermal energy, or the transfer of energy between objects. And it's between objects that have different amounts of thermal energy or different temperatures. It has units of energy, so things like joules, calories, kilowatt hours, stuff like that. And we can calculate or measure heat. So if you drop a cold piece of ice into a cup of warm water, we could do a calculation, once we learn the equations, we could do a calculation of how much heat is transferred, and we could actually predict what the final temperature of the water would be if the ice melts completely. It's not an easy calculation, but we could do it. It's kind of fun, which means it's difficult. Temperature is a measure of the thermal energy of matter. Some heat is exchanged because of the ways that we measure thermal energy typically. There's maybe a way where you can do it without doing that, but like the thermometers that we're used to using where you actually have to like stick it into your mouth or a liquid or somewhere else, there's typically some heat exchanged or heating up the thermometer. But strictly speaking, temperature is just the measure of the thermal energy. It's not actually the heat exchange. The heat exchange is just to get a measure of the temperature. There are 3 different temperature scales. There's the Fahrenheit scale, which we know and love, that has degrees Fahrenheit. So this little floating, looks like a 0, but it's not, the degree sign Fahrenheit. In the Fahrenheit scale, I don't know what the room temperature is in here, but we can find out. It's 73. So the room temperature in this room is 73. Typically, you'll see the room temperature kind of varies a little bit. 75 is often cited as room temperature, but room temperature is just whatever the temperature of the room is. So 73 today. That's a joke, partly. On the Celsius scale, this is what most of the rest of the world uses. Room temperature is about 22 degrees Celsius. And the Kelvin scale is a separate scale. It's actually just a shifted version of the Celsius scale. So the Kelvin scale doesn't use degrees, it's just kelvins. And it assigns 0 Kelvin to the coldest temperature possible, which is absolute 0. So the absolute coldest that anything can get is 0 Kelvin. You can't get negative Kelvin. You can get negative Celsius, you can get negative Fahrenheit. And also on the right, we've got this diagram that shows us freezing point, boiling point, and body temperature for Kelvin, Celsius, and Fahrenheit. I've heard it described that Fahrenheit is how we feel about temperature. So 0 is very, very cold on the Fahrenheit scale, and 100 is hot on the temperature scale, the Fahrenheit temperature scale. Celsius is how water feels. Not that water actually has feelings, but if it did, 0 would be very cold. That's the freezing point. I'm just going to write FP. Freezing point of water is 0 Celsius, and 100 is very hot on the Celsius scale for water. This is our boiling point for water. You should know both of those for Celsius. I think that's easier than the Fahrenheit scale, because for Fahrenheit, our freezing point is 32 degrees, and our boiling point is 212, and that doesn't intuitively make sense to me. And then normal body temperature is also in there. One thing that I would like to point out, not that this is necessarily important, but our Celsius scale between the freezing of water and the boiling of water is 100 degrees. On the Fahrenheit scale, it's 180 degrees. And if we look at the freezing point of water, they're off by a factor, or by 32 degrees between the two of them. I'm pointing those out, that 180 to 100 and that 32 to 0, because we'll see those numbers pop up in our temperature conversions. Okay, here's those temperature conversions. This is just one layout, one way that we can do temperature conversions. So this top one we're converting from degrees Celsius to Kelvin. This bottom one we're converting from degrees Fahrenheit to degrees Celsius. There are opportunities where you'll also need to go the other direction, and so you'll have to rearrange them. But first, before we forget about that 32 and that 1.8, that 180, here they are in action. So for our conversion from Fahrenheit to Celsius, we've got the 32, it's the difference in the freezing point of water for the two scales. And this 1.8 is the ratio of degrees Fahrenheit to degrees Celsius. So the actual units are different sizes. Degrees Celsius are a bigger unit than degrees Fahrenheit. That's mostly just like for fun knowledge. I think that's where the numbers come from, like when we're doing the actual conversion. So if you've somehow forgot and you could remember that the freezing points are 32 degrees different, and that the difference between freezing and boiling is 180 or 100, you could actually come up with the formula yourself. Not that I expect you to do that. You'll have this version of it given to you. Okay, if we want to convert the other direction, So let's say that we want to go from degrees Celsius to degrees Fahrenheit. We need to do some algebra. And this is some algebra where you could very well easily mess up if you haven't been doing algebra for a while. So we have to rearrange this bottom equation so that degrees Fahrenheit is by itself. We're going to move this 32 over. We're going to move this 1.8 over. We have to do one of those first. Who knows which one we do first? Multiply, yeah. So the 1.8 we have to move over first. So degrees Celsius equals degrees Fahrenheit minus 32. It is important that you use the parentheses unless you're using the actual, like, your calculator lets you put in stuff above and below. You do need the parentheses. So there's our 1.8. We'll just multiply both sides to move the 1.8 over. So that gets the 1.8 to cancel out. And then we've got 1.8 times degrees Celsius equals degrees Fahrenheit minus 32. So we would add 32 to both sides to move the 32 over. And we would be left with 32 plus 1.8 times degrees Celsius equals degrees Fahrenheit. You don't need any parentheses for that. If you do them in the wrong order, if you move the 32 over first, you've not done the same thing to both sides, technically, so it would end up being a different equation. You'll get the wrong answer. Part of why I pointed out. Questions about temperature so far? All right. Let's say we want to convert 47.5 Kelvin to Celsius. We had Kelvin equals degrees Celsius plus 273.15. We're starting with Kelvin and converting to Celsius. So we want Celsius on a side by itself. Pretty easy work to move this 273.15 to the other side. We'll just subtract it from both sides. And so we get Kelvin minus 273.15 equals degrees Celsius. So 47.5 minus 273.15 equals degrees Celsius. So our answer is negative 225.65. I would probably turn that into negative 225.7 with units of degrees Celsius. All right, let's say we want to convert 451 Fahrenheit to Celsius. The equation is degrees Celsius equals degrees Fahrenheit minus 32 over 1.8. So plug in Fahrenheit 451 and see what you get. Who's got something? Who's got a number they'd like to share? 233. So you would have gotten 232.7. That 7 repeats forever, degrees Celsius. And then we would have rounded for 3 significant figures to make it 233 degrees Celsius. If you got 433.2 repeating as your answer, that means that you forgot parentheses when you put it in your calculator. So you would have put in 451 minus 32 divided by 1.8, and your calculator does this first. So hopefully nobody got that, but if you did, that's an understandable mistake, and that's where it came from. All right, I'm going to just trust that we can combine those two equations together. Not like literally combine them together, because that's efficient, but also I don't expect you to be able to do that. Just, I think you can do one conversion and then another right after it, so we're going to skip that. All right, if we're changing temperatures, then we need to know something about what's called heat capacity. So all substances, any substance, is going to change temperature when they're heated or when they're just sitting out. The amount of change varies. So for example, if you get a plate of food at a restaurant, you order a meal and all of your food comes out all at once. Let's say you get a steak, you get some potatoes, you get some asparagus. Those are all going to cool down at different rates. There is like a best order. If you want to eat everything hot, there's a best order to eat certain foods at restaurants. Things like potatoes, things like rice are typically going to stay hot for a long time because they've got a lot of water in them. Veggies, I would expect asparagus to cool down quite quickly because it doesn't have quite as much water, and steak will also cool down typically a little bit quicker. Also, if you go and heat something up in the microwave and you've got like different things in there, you're not microwaving your dishes separately, sometimes you'll get one piece of food that's like super baking hot, like if you've got a piece of meat on top of potatoes, that meat's going to be super, super hot and your potatoes might still be cold, just because of the amount of heat that it takes to heat those things up. So that's just an example of heat capacity. There is a quantity called heat capacity that you can measure. So heat capacity is the amount of heat, typically in joules, required to change the temperature of a given amount by 1 degree Celsius. This given amount can vary. So it could be 4 grams, it could be 500 grams, it could be 75 grams. Any number that you want, you could put there for heat capacity. And that's not very helpful because we are typically going to have a different amount of grams than whatever that heat capacity is written for or measured for. So we are instead going to use specific heat capacity. Specific heat capacity says specifically 1 gram of the substance. That's the specific part of it. It's still the amount of heat. So it's the quantity of heat. How much heat does it take to change the temperature? This time we've specified 1 gram of the substance, and we're changing it also by 1 degree Celsius. And it's got these fun units, joules per gram degree Celsius, which is joules over grams and also over degrees Celsius. Water has a very high specific heat capacity. That's why the game hot potato works. Potatoes have a lot of water in them, and so when you heat them up, the potato stays hot for a long time. So you can toss it around for a while and it's still like burn your hands hot. You wouldn't be able to do that with I can't think of a good food that you wouldn't be able to do that with, but there's lots of foods I'm sure that would be bad for that. Like you wouldn't play hot steak with your friends. So water has a very high specific heat capacity. This is some specific heat capacities. If you need a specific heat capacity on the exam, you'll be given this specific heat capacity. You don't have to memorize these. If you were going to memorize one, I would say that water is the one to know, 4.18 joules per gram degree Celsius. A lot of these are much lower. So that's for water that's liquid. Aluminum and copper and gold and other metals have specific heat values that are below 1. So that's pretty common. Metals are generally below 1 for their specific heat capacity. Some world applications, some weather applications for specific heat capacity. The average high temp in August in San Francisco is 68 degrees Fahrenheit. In Fresno, it's 98 degrees Fahrenheit. I would guess it's about the same here. And the reason for that, or one reason for that, is because San Francisco is out on the coast and it's surrounded by tons of cold water, millions of gallons of cold water. And all of that cold water makes a very big heat sink. So all the sun's rays that come in and heat up the land, heat up the buildings, the heat that the people and the buildings produce can get absorbed by the water that's nearby, since San Francisco is a peninsula, so it's got water on 3 sides. We do not have that here. We do not have vast amounts of cold water that are around us. We've got lots of land that's dry and doesn't have a very high heat capacity. And so the heat doesn't have anywhere to go, and so everything just kind of heats up. In San Francisco, the water absorbs a lot of that heat and it slowly heats up, but because there's so much of it and it's already so cold, San Francisco just tends to be colder or more temperate. So like in the winter, it would be the opposite. It would stay warmer in San Francisco because the water helps insulate. Another way that you can observe this is if you're driving by a cornfield at night, especially if they've just watered and there's a breeze coming out of the cornfield, you'll feel the temperature drop like noticeably, like it could be 10 degrees colder because of that. So that's kind of fun. The equation that we use for specific heat capacity is this: Q equals mc delta T. So Q is heat, typically in joules or kilojoules. On the exam, you'll be asked for a specific unit. So you have to make sure that you give the correct unit. The mass is typically in grams. The specific heat capacity is in joules per gram degree Celsius. And the change in temperature is degrees Celsius. This delta symbol means change in whatever the thing is that comes after it. And so we have like a sub-equation for this. Bless you. Where our change in temperature is the final temperature. This little sub F means final, minus the initial temperature. You can have a positive delta T. That just means your temperature went up. You can have a negative delta T. That just means your temperature went down. If you're given a temperature, this is a fun trick. If you're given temperature values that are not in Celsius, that are in Kelvin instead, the delta T will be the same because Celsius degrees and kelvins are the same size. You can always convert them though instead. It doesn't really matter. Any questions about temperature, specific heat capacity so far? All right, let's do some examples. Question, what quantity of heat is transferred when a 150.0 gram block of iron metal is heated from 25 degrees Celsius to 73.3 degrees Celsius? And, follow-up question, what is the direction of heat flow? What are we finding in our first question? Yeah, we're finding heat. It doesn't specify units, so we can do whatever we want with units. We'll probably just keep it in joules. We are given that it's a 150 gram block of iron. The iron part is important, so we can go look up the specific heat capacity. So we'll find C for iron. I'm just going to be jumping back up to our table that we saw earlier. And it's heated from 25 degrees Celsius to 73.3 degrees Celsius. The from here lets us know the 25 degrees Celsius is our initial, and 2 indicating that 73.3 is our final. So you've got some directional indicators. When we've got a bunch of things, like we have with this problem, it can be helpful to list out what all of our variables are. Pull them out of the question problem. So our mass is 150 grams. Our initial temperature is 25.0 degrees Celsius. Our final temperature is 73.3 degrees Celsius. And since we just saw them for the very first time, Q equals mc delta T, and delta T equals TF minus TI. That's kind of most of the things that we need. We also need that specific heat capacity. So let's go back and find that for iron. For iron, our specific heat capacity is 0.449. So C of iron, 0.449 joules per gram degrees Celsius. So now in our equation, our Q equals mc delta T, we were given M, we looked up C, we don't have delta T, but we have an equation for delta T, and we have TF and TI, so we can solve for delta T. So our change in temperature is our final temperature. That's the 73.3 degrees Celsius. Minus our initial temperature, the 25.0 degrees Celsius. And because we don't feel like doing that math in our heads, we'll ask our calculator to do it for us. Calculator says this is 48.3 degrees Celsius. What does that mean? What does delta T equals 48.3 degrees Celsius mean? The change was 48.3 degrees. It's positive, so that means the temperature went up. So temperature went up 48.3 degrees Celsius. And we're going to plug that into our Q equals mc delta T, since we just calculated our delta T. So Q equals our mass of 150.0 grams times our C value with units of joules per gram degrees Celsius times our newly found delta T, 48.3, degrees Celsius. Our units of grams cancel because we've got grams on the top, we've got grams on the bottom. Our degrees Celsius will also cancel out for the same reason, one on top, one on bottom. And we're left with units of joules. So we'll put this whole thing into our calculator, 150 times 0.449 times 48.3, and we get 3,253.005. with units of joules. We would have to round this for 3 sig figs, so this turns into 3.25 times 10 to the 3 joules. Questions about the calculation part? Okay, and then thinking about our block of iron, what's the direction of heat flow? Is it exothermic or is it endothermic? Endothermic. Why is it endothermic? Yeah, it's increasing temperature. Temperature goes up, and Q is positive. So our joules here has a positive in front of it, secretly. It's not negative, so that also means that it's endothermic. This is the amount of heat, the amount of joules that the block of iron gained, that went into the block of iron metal. Questions about that? Cool. A large block of ice absorbs 858 kilojoules of heat as it warms from negative 37 degrees Celsius to 4 degrees Celsius. What is the mass of the block of ice? So we are going to need our Q equals mc delta T Tf minus Ti, and our C of ice we'll need as well. Boop. It's 2.06. joules per gram degrees Celsius. I'll give you a couple minutes to work on this with your neighbors, and then we'll go through it quickly. All right. So as I mentioned, if you're getting 10.15 grams, it's not correct. You missed a step. You maybe didn't write your units and cancel them out. So let's take a look at how to get the correct answer. So for our question, we're trying to find the mass of the block of ice, which is the m in the Q equals mc delta T. So we could start off with just rearranging to get m equals Q over C delta T. We divide both sides by C delta T, flip it left to right, and that's how we get here. In our question, we are given an amount of heat, 858 kilojoules of heat, as it warms from negative 37 degrees Celsius to 4 degrees Celsius. The negative 37 is our initial, the 4 is our final. So our delta T is going to be 4 degrees Celsius plus 37 degrees Celsius, because we're subtracting a negative, so it's a double negative, so we're adding them together. We're looking at what's the total distance traveled, and the distance from negative 37 degrees Celsius to 4 degrees Celsius is 41 degrees Celsius. So our delta T is 41 degrees Celsius. So if we plug in 858 kilojoules over 2.06 joules per gram degrees Celsius, and our delta T, 41 degrees Celsius. If we look in the bottom here, we've got delta, or degrees Celsius, that's on the bottom of the bottom, and degrees Celsius that's just once under there. Those will cancel out. The grams is all the way down here. It's the double under, so that flips to the top. I don't really know how much better to say it than that. And then if we look at our other units, we've got joules on the bottom. In our denominator, we've got kilojoules in the numerator. So kilojoules on top, joules on the bottom. Those aren't going to cancel out exactly. Now there's one neat trick that we can do, but don't confuse yourself if you're going to use this one neat trick. That one neat trick is that we can actually just cancel the joules part and leave the kilo behind. If we do this, the units that we get would be kilograms. And the problem didn't specify what units to use for the mass, so we could answer in kilograms, and it would be that 10.15 and change answer for kilograms. If we wanted it in grams, we've got a couple options. We could turn this into grams by multiplying by 1,000. Or we could have converted away this 858 kilojoules, turn that into joules. So that would look like, duplicate. That would look something like, too many things. This. Multiply by 1,000. Now we've got joules on top, joules on bottom. Joules cancel. As previously mentioned, the grams flip to the top, and we get that 10,158.6 ... grams. So you can use that one cool trick. Sometimes there's an extra cool trick that you can do because you'll have the same prefix on the top and the bottom, and so you can cancel out the prefixes. That's fun. Or the safer option is to just go ahead and get rid of the kilojoules, turn it into joules first before you put it in, so you don't accidentally miss your metric prefixes. Questions at all? Then that'll do it for Chapter 2.